Hey, welcome back. In this video, we're going to start discussing how to prove things. When we prove things, we're always going to have some list of assumptions. Other names for these assumptions are premises or hypotheses. And we'll also have a conclusion. All of these things, the assumptions and the conclusion, will be propositions. In order to get from the assumptions to the conclusion, we're going to use rules of deduction. So we're going to start with the assumptions, and we're going to use rules of deduction to prove other propositions from those assumptions. And we might have to use the rules of deduction repeatedly until we can get to the conclusion that we're trying to prove. In this video, we're going to focus on the main rules of deduction that you would use in a proof. And hopefully, most of them will seem very intuitive. It's possible that you've already used some of them before. The one we're going to start with, if there's any whose Latin name you've heard of before, this one is probably it. It's called modus ponens. And what modus ponens says is if we know that some proposition P is true, and we know the implication P implies Q is true, then we can conclude that Q is true. With all of these rules of deduction, I'll show you a simple example of how we would apply the rule in a step of some proof. And I'll also mention, for this rule of deduction and for the others, all of them you can check to see that they're true by doing a truth table. The truth table that we would do for this one is P and P implies Q together imply Q. And if you do a truth table for that, you see that you get a T in every row. But since we've done a bunch of truth tables in the past videos, I won't do the truth table in this video. So here's an example of using modus ponens for a step of some proof. Suppose the step is, we know that if C is odd, then C squared is odd. And suppose one of the other things we know is that C is odd. Then we can conclude, for the next step of our proof, that C squared is odd using those last two bullets and modus ponens. Another rule of deduction with a pretty famous Latin name is modus tollens. For this one, suppose that we know not Q is true. Suppose that we also know, like last time, that the implication P implies Q is true. Then we can conclude that not P is true. And like the last one, you can check this just doing a truth table for the proposition not Q and P implies Q together imply not P. And you can see each row you get a T. Here's an example of an application of modus tollens in a step of some proof. Suppose we know if C is odd, then C squared is odd. Suppose we also know that C squared is not odd. Then we can conclude that C is not odd. And this is using the last two bullets with modus tollens. So our next rule of deduction is called transitive implication. Suppose we know that P implies Q is true, and suppose we also know that Q implies R is true. Then we can conclude that P implies R is true. And like the other rules of deduction that we saw, you can check that this is true by doing a truth table for the proposition P implies Q and Q implies R together imply P implies R. And you should see that all 8 rows of that truth table have a T in the column for the proposition that I just said. So let's look at an example of transitive implication. Suppose that we know that if C is odd, then C squared is odd. And suppose we also know that if C squared is odd, then C cubed is odd. Then we can conclude if C is odd, then C cubed is odd, using the last 2 bullets together with transitive implication. The next one is called disjunctive syllogism. Suppose we know that not P is true. And suppose we also know that P or Q is true. Then we can conclude that Q is true. And like the others, you can do a truth table for this one. And you can see that each row you get a T. And this one will have 4 rows because only 2 propositional variables. For example, suppose we know that C is not odd. And suppose we also know that C is even or C is odd. Thus, we can conclude using disjunctive syllogism with the last 2 bullets that C is even. Our next one is probably going to seem even more obvious than the others, maybe even pointless to mention, but it gets used sometimes. It's called trivial disjunction. If we know that P is true, then we know P or Q is true for any proposition Q. And like the others, this is something that we can check with a truth table. This one will have 4 rows. Every row will have a T in the column for the proposition P implies P or Q. For example, suppose we know C is a multiple of 3. Then we can conclude with the trivial disjunction that C is a multiple of 3 or C is even. Here's another one that is going to seem similarly trivial. This one we can call single conjunct. If you know that P and Q is true, then you can conclude that P is true. And we can check that with the truth table. The truth table P and Q implies P. So for example, suppose that we know C is odd and C is a multiple of 3. Then we can conclude that C is odd. So sometimes in a proof, you might know multiple things about some element, and you only need to use one of those things for some part of the proof. So that would be a time where you would use this, and it would make sense to use it. Here's one that gets used plenty of the time, but usually when we use it, we wouldn't even mention it. In fact, most of the things I mentioned in this video, when you read a math paper, none of the uses would get mentioned. So this one we could call commutative disjunction. If we know P or Q is true, then we can conclude that Q or P is true. And you can do a truth table for that. P or Q implies Q or P. So for example, suppose that we know C equals 2 or C equals 3. Then we can conclude that C equals 3 or C equals 2. A similar one is commutative conjunction. If we know P and Q is true, then we can conclude that Q and P is true. And we can check this by doing a truth table for P and Q implies Q and P. And an example, suppose we know C greater than 2 and C less than 3. Then we can conclude that C less than 3 and C greater than 2. Now we're going to see some different kinds of rules of deduction. So the ones we saw on the last several slides didn't have any quantifiers involved. The ones we're going to discuss now are all about quantifiers. There's only a few of these that we're going to see, and some of these rules you might have used in the past. The first one is called universal instantiation. So we have some proposition of the form for all x, p of x. And suppose we know that it is true. Suppose we know it's true in a universe that is non-empty. If we know these two things, then we can say for any element C in the universe, we can say that P of C is true. For example, we know every natural number n has the property that n is greater than -1. We can do a universal instantiation on that proposition in that last bullet. We can instantiate it with n equals 0. And our conclusion is that 0 is greater than -1. 0 is a natural number. We also have an instantiation rule for the existential quantifier. Suppose we know that exists x, p of x is true. By definition of the existential quantifier, exists x, p of x means that there exists some x in the universe for which p of x is true. That means that there has to be some element C in the universe for which P of C is true. And that's what we claim in that second bullet right there. So for an example of existential instantiation, suppose we know there exists a natural number n such that n times 2 equals 2. Then if we're in some proof, we can say, let C be a natural number such that C times 2 equals 2. And then from that point onward in the proof, we can just work with C. And that is often useful to do in proofs. Here's one. And for this one, it appears that the title has a typo. So I'll correct that right here. It should say universal generalization. So we already saw universal instantiation. This one is universal generalization. So universal generalization, it might seem a little less obvious than the two instantiation rules. So when we do universal generalization, we know that P of C is true for an arbitrary C in the universe. I want to circle that word arbitrary. It's very important here. What do we mean by arbitrary? Well, we mean what I mentioned in the parentheses there. We're making no assumptions about this C other than the fact that it is an element of the universe. So our assumption here is just that P of C is true for this arbitrary C, where arbitrary means what I wrote in the parentheses. And if we know P of C is true for an arbitrary C, then we can conclude that for all x, P of x is true in the universe. So maybe this one seems a little weird, but we can think about something that we did a lot back in Algebra 1 and Algebra 2, back in high school. And here's an example that will hopefully illustrate it. So back in algebra, we did some expansion of polynomials. So you can take some polynomial c plus 1 and raise it to the third power. And that gives you c cubed plus 3c squared plus 3c plus 1. And this is true for any real number c. So c plus 1 cubed equals c cubed plus 3c squared plus 3c plus 1 is true for any real number c, regardless of what c is. The only assumption there is just that c is a real number. And based on that, based on the arithmetic we did to multiply that out and conclude that equation, just using that single c, we can conclude with the universal quantifier that for all x, x plus 1 cubed equals x cubed plus 3x squared plus 3x plus 1. That proposition is true in the universe of the real numbers. So that's a typical example of universal generalization. And that's something that we used a lot back in Algebra 1 and Algebra 2. We proved a lot of equations involving variables x or y. And most of those equations would have universal quantifiers in front of them, sometimes restricted universal quantifiers. So our next rule is existential generalization. So we already did existential instantiation. And this one works pretty much in reverse of the existential instantiation. So in this one, suppose that we already know that P of C is true for some C in the universe. Then we can conclude that the proposition exists x, P of x is true in the universe. And here's an example. We see that 1 times 2 equals 2. So here our C equals 1. And we can use that to conclude that the proposition exists X such that X times 2 equals 2 is true in the real numbers. And it's also true in the rationals and the integers and the natural numbers. And that brings us to the end of this video. Thanks for watching. In the next video, we'll see some basic proof methods.